Okay, let's start. Good afternoon to everyone, faculty and visitors from far, and in particular also the students. Appreciation to the students who made it today and who made their way also here to this exciting talk that we're looking forward. Thank you to Dean Maria Pervolini, who are supporting our lecture series and encouraging every year inspiring dialogues. And I also want to thank our proud lecture committee chair for delivering. You're supposed to clap here. I wanted to say for delivering multiple semesters of a now widely known lecture series and talks with renowned and international guests like today, and also for having recently given birth to her beautiful daughter, Sophia. I thank our tireless committee colleagues, Andreas also here, and the SoAD staff who are working countless hours to make visits like today in-person reality and also as frictionless as possible. So today's topic is new materials, processes and additive manufacturing. And while our own new 3D printing XL lab in Ed Hall in Long Island is soon poised to open. Let's say at least in May for the setup. What a great occasion to have a well-known colleague here speak today about his experience in the labs. Interesting things happen typically, as you know, at the fringes or at the overlaps, right? So I'm saying a few of those that pertain to a visitor. First, I'm not sure how to describe it better, but I see him as a structural engineer slash designer, because I consider him working in this kind of hybrid fashion where digital technology injects creative experiences in this kind of back and forth between field work, research, and teaching. He says, I'm passionate to unify material, processing, and form in construction. I'm sure you see a diagram soon coming up. Now, let me give you some professional highlights, those he will not mention today. So initially, he worked as a lead engineer for one of Germany's famed practice, Bollinger and Grohmann. And you play the key role, now when we look back, in the pioneering freeform architecture. Think about Greg Lynn, think about Hanish Kapoor, and think about the Kunsthaus Graz by Colin Fournier and Peter Cook. Any one of my students here who know Peter Cook? Hands up. 1, 2, okay. If not, please look him up. Arch Daly calls the building the alien among historic landmarks. Then he worked on a project by Bernhard Franken, who's a common friend of us in Frankfurt. And you might know the IAA. It's kind of the world-renowned German automotive car show, if you're into cars. And the two projects, one was the so-called BMW bubble in Munich. That was in 1999. And then later the BMW Dynaform, each with a kind of a non-linear structural rib design, I might maybe call it. So for the students here, if you want to look it up, the wave is really important to know. Shortly after, in 2002, he, together with Klaus Fett and Sigurdur Gunnarsson, co-founded the Office for Structural Design, OSD, a structural engineering company with location in Frankfurt and Hamburg. And they received many accolades, I would say, for their brilliant expertise in structural design, facade design, and sustainable construction, because, as he calls it, innovative engineering solutions, deep material knowledge, and a focus on resource efficiency. Then there's academia. So for a long time, so when he worked for 20 years in the business, like many of us, he straddled certainly this kind of exhausting, nurturing, but also multifaceted relationship between professional practice and academic research. Now, already having done several, let's say, news-shattering build projects in Germany, he became a visiting professor at the Städelschule in Frankfurt. known at the time, I would say, for the architectural classes. Again, Peter Cook maybe comes up as a name, and also Ben van Berkel. And I remember at the time, Johan Bettum was, I think, the acting head, it was called. And they invited me to give a lecture there in 2006. And we finally had an occasion to meet in person for the first time. We had some discussions on the phone for projects before. And we started to talk about this kind of pros and cons, I would say, of professional practice, academic research, and this kind of avenues, this emerging digital fabrication that kind of started to kind of become a big topic at the time. And I was just off later to go back to Texas and develop a digital design and fabrication lab. Little did we know at the time about looking into academia to gain more time for research. And I remember when I visited him in one of the first labs that he developed, CNC machines, laser cutters, early 3D printers. And he was just starting to teach, TU Kaiserslautern. He built a lab, then he went to TU Graz, another lab, and always developing new digital infrastructure and machines and equipment to do the research we wanted to do. So we had something to share, really. Luckily, since 2011, he has been, let's call it, stable, a professor for structural design at the TU Braunschweig. Again, initially, he developed his first large-scale lab with German DFG grants. And I have a little anecdote to that too. So I worked extensively in Italy with natural stone, and I basically know all the large CNC manufacturing companies. And so we had somehow an overlap because we wanted to find a company that I could build a custom equipment for his lab that would be like a massive CNC gantry machine that typically cuts stone. And why we don't hang a little Stäubli robot on that machine, and suddenly we can do a lot of cool things, right? So we could print, spray, scan, and then I think shotcrete came into his head and said, we have to try this one. Yeah. So this was really the beginning of his amazing work that he's going to show today from the interdisciplinary research at the Institute for Structural Design, ITE in Germany. And I know that the most recent one is also, there is somewhere, I think, and he will maybe confirm in the lecture, a cobot in one of his new labs, so a larger scale. And I'm sure he can talk about that, how that came to birth. And since 2020, he is also the lead of a very powerful, I would call it, German collaborative research center, the TRR 277, Additive Manufacturing and Construction, that combines knowledge and expertise from two of maybe the most important German universities, so Braunschweig and Munich. So really amazing. So ladies and gentlemen, please welcome Professor Dr. Harald Kloft to a lecture here.
Yeah, thank you very much, Christian, for this really kind introduction. I forgot most of this stuff, what I all did. And yeah, it's I'm very pleased to be here and like to present some of our newest work. The interaction of material, process, and form in additive manufacturing construction. I choose this title, and this is exactly what you track. So as an engineer, you are, of course, used to work with material and in the relation to form. But what I will show and focus today is that we now also have to take care on processes again. And so let's start. Where is the other one? Down there. Yeah. So easily you could say construction is to bring material into form, and the processes are the technological link. And what is important for me is always when we look forward and trying to step forward, that we also look backwards. So it's not to step backwards, but we have to see where we are coming from. And for that, it's really important to start on reflecting material. So when we go far away from our today's date in the Earth history, then natural stone as anorganic and in a hardened and granular state is one part of the material earth delivered, and the other is organic materials. And with both, traditionally, we are used to work. And the settlement of human beings, you can say, is around 10, 12,000 years ago. But the stones we used at the beginning, so they are formed in hundreds of millions of years sometimes. So this is the total different time scale, the material we work with, and our being here on the planet. And I like to reflect this, that at the beginning we settled there where we had on one side the environmental conditions, but also where we had the material available. And so we took subtractively the stones from mountains and used them then in a format we did manually. And they had an enormous amount, because this was manual labor, and also the transportation was difficult. And thinking on circular economy and circular construction, so even they were used, were taken as spoils of war, and they were used again in other environments, as so-called spoliar masonry. And to start with natural stone to construct means also that the design of architectures and structures is a kind of process to find the right forms itself. So here you see the development from the Greek to the Roman arch. So because of the less tensile strength of the stone material, so it has a high compressive strength, but really low tensile strength. So today we are used to have free-span open spaces, but here every 5-7 meters there was a column. So a huge space was full of columns, a totally different kind of design. And the Romans, they found the arch and could span slowly over greater or bigger distance. And this refining the knowledge and the unity of material, process, and form is a continuous process. And the Gothic architecture is maybe the most filigrane expression of dealing with stone as mass active structures. And when industrialization began, so suddenly we were able to produce technically new materials like iron, and later on I will show also concrete, of course, but the forms we had to develop new. So the first bridge, the Colebrookdale Bridge in England, looks like a typical stone bridge, but without stones, because it was not known how for this material new shapes have to look like. So also this was a process. It took continuously research and development to find the new logic of form for iron and later on steel construction, like you see here the third and fourth in Scotland. Concrete in the beginning of the 20th century was the second material, which is still up today and is the most used material up today. And here we were able to form the objects on site. So the high impact energy was done in the cement production, but on site you could, with low energy, by the hydration process, design and bring new shapes into construction. And the secret behind is cement. This is what we discussed today a lot, because it needs more than 1,000 degrees to burn limestone and other ingredients to the so-called Portland cement. And this needle-shaped hydration, which encloses the granular material, is the secret that we have this high compressive strength of concrete. But the disadvantage is when we deconstruct buildings that we don't get back this origin granular material. So there's always wasted cement lime on the broken small particles. But concrete alone wasn't the innovation. The real innovation was the integration of the reinforcement and the composite material of concrete and reinforcement as reinforced concrete. And so this is why then concrete shaped into ingenious masterpieces, like here the bridge of Robert Mayer, the Salguero Bridge, or the Palazzetto dello Sport by Piero Vicinelli. However, industrialization also began very early in concrete construction to prioritize the process efficiency over the material efficiency, accompanied by formal limitations and inefficient material usage. And you see here that up to date, this is our standard in construction. So standardized processes and pre-processes, which are dominating construction. And this complements, the symbiotic complement of material, process, and form got slowly lost. So as engineers and also architects, we have in the last decades developed a lot of advanced materials, ultra-high performance concrete, fiber reinforced concrete, and so on. And we have sophisticated computation design and form finding methods. But we didn't take care really on new processes. So what we are missing is the link between material and form. And this is what we have to where we had to work on. And if you look, for example, in the technological progress in car industry, there is a continuous development over the decades from industry 2.0 to today's industry 4.0. So the networking of machines, processes, and people. And it's also obviously in the car design. So the first Carl Benz car, it's more how you say, a horse than a car, and on the right side is the newest car development today. And in construction, you see on the left side already more than 100 years ago, the system formula was invented and the integrated reinforcement. And this is still how we work today. And this is also how we see in our architecture. So the progress in building, this is in Berlin, the Berliner Gründerzeitbauten, beginning of the 20th century, and this is what we build today in Frankfurt. So you can decide what you like more, what kind of design. I would prefer the left one. But new forms in architecture, Christian already mentioned, I will show a little bit, is not new. So new forms in architecture and new developments, in my opinion, began with the museum by Franco Gehry in Bilbao, the Guggenheim Museum. And what was really new? So Franco Gehry was already over 60 years when he won this competition with his sketches and models. And he was not able to build before because those sketches were no basis for construction. So we could not run a construction or a planning process, better said. And so the innovation was twofold. One was a new method to digitize the surface of physical models by using this dot-by-dot scanner in that time. And so they had initial digital models which were not really continuously. So there were a lot of, you see it here, a lot of failures, so was manually work to do afterwards, but it was a digital model. And the second innovation was then with this digital model to use the parametric engineering software CATIA from the aircraft industry, which were then the basis to really handle these complex geometries and make it buildable. And like Christian said, I was lucky in that time to start my professional career after my PhD in the office of Bollinger & Kromann, and I had immediately the chance to work on the BMW pavilions in 1999. And in that time, there was this kind of freeform architecture was really advanced. And but when you reflect today, then this is a different thinking. So we started immediately from having a form, and we were on the search for material and processes. So it was for the engineers opposite thinking. We were used. You start with either you know in a normal building what to do, or you come from the material and process to a form. But here it was the opposite direction. And Gehry, he did the inside and the outside layer definition by physical models and by scanning the surface. And so for me as an engineer, so when we worked on this one museum in Erfurt in Germany with Geary, so we had then the task, this was defined by the architects, there was no discussion about it. So this was the outer and the inner surface, and we had to look for the space where we can integrate our structure. So it's not a normal structural design process, it's more a process on geometry. So we really had to, using Rhino, and to look for geometrical spaces where we could integrate profiles. And this is, of course, something which is highly complex and is interesting, but it's not structural efficient like we used to work as engineers. A little different than in the project with Bernhard Franken. This was the first complete digital process. So here was not a scanning process of a physical model, the initial geometry and definition. It was defined by Maya, and 2 water drops for this exhibition pavilion running to each other and meeting in one point, and then he has the form frozen. And we used ANSYS, finite element software, to calculate, and also CATIA then to handle the more than 300 different blades on the surface. So again, here we had to search for what kind of material you could bring with which process into this form. And here we did also the whole fabrication process was CNC based, so the molding, the 5-axis milling machine of the molds. Then the blades were cutted also with later on with a 5-axis machine, and the water cut, 3D water cut for the aluminum profiles, and all assembled together on site. Just for 2 weeks. It's a pity because a lot of work in it, and when everything is digitized, you can repeat the process. So we always said you could do 100 of this, or 10 in everybody, 10 of this could be sold in the world, and there would be maybe a market, but this was exclusively done. But without the bubble, it would not be possible to build the Kunsthaus Graz. So this was, let's say, kind of preliminary work for doing finally the Kunsthaus Graz by Peter Cook and Colin Fournier in 2003 for the capital city of Europe. And you see here again, so we had to bring industrial products, steel profiles, plates, and so on, all in this 3-dimensional shape. And at the end, it was like defining or designing a 3D puzzle. Rhino was used to do collision control, what is today a standard topic in building information modeling, what we did in that time. And for me, the bird's nest in 2008 defines a little bit a boundary, because this is so much steel, wasted steel here from an engineering point of view, and a lot of manual work, labor. And so we saw in one, let's say, this was a turning point where we saw this kind of process is not what we could adapt in construction, what has really a future in construction. It's for one building running such processes, not repeating the process again, is really not economical. So for a few years, customers, they really liked this fancy architecture, but when they at the end had to pay the bill, so then slowly it was then out of the discussion to go in this direction. And when you look today, this is a picture I took 2 years ago in Frankfurt. So this, I mean, maybe your construction sites here in New York, when I see around cleaner and more organized, we have really sometimes such kind of construction sites, and at the end, customers pay for the apartments 10, 12,000 euros per square meter. Okay, for here it's maybe cheap, for Frankfurt it's expensive, but you see there is an inefficient material use. It's a lot of high environmental impact and also waste. We produce low productivity, the lack of skilled workers we have, but also a lack of quality and safety at work. So the question is how to continue the construction. And here is a nice image which I always also like to bring into your mind, that it's not just a thing on technologies, it's also that the world population from 1950, from 2.5 billion, today we are 8 billion people, and so we need more and more resources, but also we have to build more. So the question is how many cars we need. This is something we could discuss, but every person needs let's say, an apartment or a roof over his head. And on the other side, also because of the high environmental impact we already have, we have to build now more structures, protective structures. So coastal protection, food protection, and so on. So you could say we should build less because of our high pollution we produce with the construction sector, but we have to build more with less resources and less emissions. So my argument is that we need a completely reset of the unifying of material, process, and form, and we have to rethink and start from the perspective of the material. So this is what is the basis, and think from the material and the process to a form, and not from the opposite direction. We consider additive manufacturing as a key digital technology for the future in construction, and I will express you now why we see it in this way. We is the Collaborative Research Center, Additive Manufacturing Construction, and Christian mentioned already, is running since 2020. And there are more than 80 people working in this Collaborative Research Center. It's funded by public money. And you just started this funding with a perspective with your topic of 12 years. So every 4 years, there is an evaluation which you have to take. But in general, at the beginning, it's clear you have to show a perspective over 12 years. So we now are in the 5th year, 25. And so we took the second review last year. And yeah, so what is additive manufacturing in construction? And this is also important for me, so that it's clear using a robot, and for example, assemble bricks like Ramazzi Kohler did when they started in working in digital fabrication. This is adding bricks, but is not additive manufacturing. So this is additive assembling. What is the difference? Here, the brick is a pre-product. The brick has an industrial pre-process, is a product, and you take a product and assemble it. This is what we mostly do in construction. But additive manufacturing is different. So additive manufacturing means that you bring material in form within the process. And this is a different thinking. So you have to be clear where you want to put material. So you design also the path planning. So you just define where you bring the material and bring it layer by layer into form. And so on one side, you save one process, a formwork process, so that it reduces the process steps in construction. On the other one, you also need to think where to apply material. So for engineers or architects, it's a different kind of design. Instead of filling the material between the formwork, you start now to design by yourself. And you never, for example, a carbon would print with a completely filled inside. So you just print the ring, so you have a hollow space, and you can use the space for post tension or for integrating technical installations and so on. And the second thing, what is also very important, it's a digital process. So by a digital process, you can digitally link to the design phase, which is also digitally, and which is actually by using building information modeling and having this handcrafted process on site, is not directly linked. In those collaborative research centers, we have different research areas, and the main one is here, material and process interaction. I show you what we mean. So we have here actually 9 projects, and we not just do research on extruded concrete. No, we have also shotcrete, which is named here spraying. We have injection 3D printing. Then we have the particle. These are depositions, so the material is mixed and you apply it layer by layer. Then the particle bed processes. There are particles in a big bed, and you activate them either by just when you have mixed the particles already with dry cement, so you just need water to activate, or if the particles are without the cement, so then you introduce the water cement line. We also have earthen material. We have fibers and filaments and metals in additive manufacturing. What is important when you do research on material process interaction and you want to have robust processes, then we do a lot of parameter studies and computation modeling and process control. So we have to work with digital modeling to get really robust processing in the end. And this is the C area, design and construction, what I mentioned before, because it's a digital process. So we have now the ability to connect the digital construction side with the digital design side by digital twinning. And this is also a new, is not that we just replace traditional construction by additive manufacturing and keep the sequential process planning and then build as planned. No, we can start much earlier to construct because we can also give information from the construction site back to planning and try to make it much interactive than it is today. So what are the KPIs of this collaborative research center? Of course, what I addressed before, 80 people, so it's a highly interdisciplinary teamwork. So engineers, architects, of course, but we have mechanical engineers, robotic specialists, material specialists, so working all together. So one is the topic itself, which you have to set up very clear. The other one is that you have to really have a strong team, and 80 people to motivate is also highly difficult job, you could imagine. And then the large research infrastructure facility, what Christian mentioned. So the DBFL in Braunschweig, and thanks again, Christian, for your recommendation of OMAC 10 years ago. So we went together to Italy to see the companies working in stone manufacturing, and so this was what they offered, this Plate 5 CNC unit, and we integrated a second portal with the SoAD robot. And it's not just that there is a second portal, it's also that we have 2 different control environments. So the CNC control environment is totally different than a robot control environment. So you marry 2 different controls, and you have to decide who is master, who is slave. And we are able now to run each of the portals independently, but also we can do collaborative processes. Then we have a smaller unit in Munich, which is still under construction now. Then we have mobile robots, which we use also integrated in the DBFL. We have also standard printers from industry for working with selective laser melting and for the selective cement activation, so for particle bed processes in general. And this is a new thing, the digital construction side at TU Braunschweig, a cobalt printer, which we have with an extruder and also on shot print portal, and 3 mobile robots working together. I'd like to show you now I also, and the research methodology, this is all also very important. So we as, let's say, architects and engineers, we are not used to do fundamental research in processes. This is not what we did the last decade. So we have to find, or we had to find, a methodology which fits. And we always start in a one-to-one proof of concept. So this is also new. Architects, if you think on Rob, what is the name? Rob Arch. So this conference is, so there are a lot of things architects show with the robots, what they can do, but then they stop. So they show the concepts, what is possible, but fundamental research means that then you have to select parameters. And parameter by parameter, you have to identify which are the mean parameters and then validate them by testing and concurrent computation modeling. And then we go back and do a demonstrator, a large-scale demonstrator. And this is what I will show you later on. So these are the large-scale collaborative research centers we presented last year in Munich. So for the different projects you see here, this is a particle by 3D printing. So it's a facade element with integrated hollow spaces for guiding the air, and also the angle is connected. Thomas Auer is working here. We discussed it before on him on the shading of the system. This is a post-tensioned bridge, small bridge with segments 3D printed. This is a joint with 3D printed selective laser melting principle. Here in the shotcrete processing bridge, a shell structural element I will show later, and also here a collaborative thing with also surface post-processing to give ornaments on the surface. I will now go a little bit deeper into our research at the Institute of Structural Design. And I like to mention that this is also very nice to be in a team with my colleague Norman Huck. So we are two professors. Norman Huck, he is an architect. He did his PhD at ETH in Zurich. Came 7 years ago to Braunschweig as a junior professor, is now a full professor on me. So we both are leading the Institute of Structural Design. And so also our team is mixed up with architects and structural engineers. Our research facilities you saw before is the DBFL and the digital construction side. And so a few of our main processes, so with steel, we work in a kind of hybrid RAM. So we try to print on serial plates or profiles, so to make them more strong, instead of just using the profile which is calculated on the maximum stressed area. We use thinner industrial profiles and articulate them by the printing. The shotcrete printing I will also show later, then also the robotic tri-joints, so using the CNC as post-process for connections, and then earth construction, robotic round earth, which I will show later. So in general, we have two strategies. So one is high-tech processing and high-tech material. So when we use high-tech processes, then we can discuss about concrete, and it's okay to give a lower CO2 footprint in the material when we waste the material and use normal formwork construction. But when we use robotic sprayed processes, so then this is a high-tech process, and we try really to minimize the mass of the concrete we use. But then it's not just allowed, it's clear that we use then a high-strength concrete. Otherwise, it doesn't make sense to use high-tech processes with low-tech material. Makes sense, but I will show later with what kind of materials. So shotcrete is in general not new. Shotcrete is an already existing technology, and this is also good because the norms and regulations are also set on shotcreting, especially in tunneling, for example. But what is new, what we did new, is we applied shotcrete to a robotic arm. And what does this mean? So we have two major features. So one is we add compared to normal extrusion, it looks similar. So you lay down the material and build up a structure layer-wise, but using shotcreting, you give compressed air here before in the nozzle, before the material leaves the nozzle. So the material gets speed up, and by this speeding up, you see the inner bond, the inner material is homogeneous. So it's quite the same, even better in testing than the normal concreted and condensed material. So it looks from outside like extrusion, but it's a totally different process. And the second thing is we give into the air material to speed up the hardening process. And so we are able to break down really the hardening process 2 minutes. Here in the mix, we have an open window, let's say, of an hour. Otherwise, it would get hardened in the pump and the tubes, which we don't like to. But then we can reduce it here in values of minutes. So depending on the objects we print. So this accelerator is, of course, another secret of 3D concrete printing. I spoke about before on the material process interaction. What is material process interaction? And here is, you see on the left side, a traditional handcraft work in stone construction. And on the right side, the robot is milling with this head of a hose. And it looks that the robot can do the process, but it's not completely, because here the worker is in this process with all his senses. So by using the hand, you feel, you get the feedback of the material. You feel how hard it is, how weak it is. You feel if it breaks. You listen, you hear. So your ears, you see, your eyes. So your whole senses are integrated in this simple process. When we do here, when we use a robot, we program a path planning for a milling process. There's no feedback. So here's the milling machine is running. It's just a geometrical process. There are no senses in. And this is the difference. So we try to get in our processes also the feedback from the material. And this is the new thing. So we have two sides which we interact with and which we control. So the material side and the process side. And this, what I was meaning with parameter studies, we have to study what are the main parameters on the process side, what are the main parameter on the material side to bring them together. And this is also why in the future, when you do this really advanced, it's not that easy just develop a new material for 3D printing and keep the processes as we were used to. No, you have continuously during the processes on site or in the factory control and work with the control of the process. So shotcrete 3D printing is by using this gantry system and the robot. So we have the 6 axes of the robot, the 3 axes of the system. So we have an enormous geometrical freedom. We can control the layer height and the speed, and this is controlling the width and the height of the layers. We can also print on cantilevering structures. We can do this gradual printing. That means that normally when a 3x printer is just cantilevering each layer, so we can really fully curve so that the section is fully able to take the forces. And we can also, by our laser scanning process, correct if there are some failures within the matrix. Yeah, this geometric freedom, also you see here, addressed again. So in the last years, we have different strategies. So on one side, we worked on elements. So we see, of course, a chance in prefabrication, in prefabricated elements. So columns, double curved walls. Here we try to work with spatial beam structures. And what is, in my opinion, also very interesting is this combination of existing processes of concreting and additive manufacturing in combination, this ribbed ceilings I present a little bit later. And in general, we have then two strategies for the reinforcement integration. So we are working on structural concrete with the shotcrete. The videos didn't work here, I don't know why, but it doesn't matter. So the reinforcement is not like in the normal formwork construction that you bring it in before concreting. So you could bring it in during the process, and either first the concrete is running, and so then you have the layer for just to deposit the reinforcement where it's needed, or the reinforcement you spend before, and then you can apply the concrete on the reinforcement I show later in the video. So here you are able maybe to make more freeforms with the reinforcement, and here you have to develop technologies how to integrate the reinforcement during the concrete process. And here you see we have different strategies, and this is also something which is you reflect slowly, so that when you do in formwork construction, remove the formwork, then the concrete is hardened. So then you want to do something, you have to bring a lot of energy to drill in holes or something like this. In the 3D printing, the concrete is still in the free state. So you can just, for example, robotically screw in the reinforcement. So it's hard enough to take itself, its own load, the element, but you still are able to, videos often working, so yeah, to screw reinforcement from each direction. And so this is also something which is new, that we can directly after printing immediately put the reinforcement in. Other strategy is that we put it in between the layers, and here you see that with computational design. So to find the main tensile lines, and the question how we can then address or we get integrated reinforcement is then based also on the concrete layer control. So these are the concrete layers we print here, and then we are able to have a kind of bed where we then position here as a carbon fiber mat. And so it looks like a normal beam, but the inner form is highly efficient. And this is also something which is form is for me a difference between shape and form. So shape is for me just the outer geometry, but form is the outer shape plus the inner structure. Yeah. These vertical videos are not working, they are turning in the opposite. So here you see, for example, how we do in a collaborative process, use just a single curved or straight wall, and we put just normal reinforcement before, and then with the second layer, we are able to imprint the reinforcement, and then immediately you could here with the running disc, we smoothen the surface. And you see here, there's really less material which is wasted. So it's an optimized process. And with this, we are able to do such a double curved wall up to 3 meter height, and in less or in 4 hours manufacturing time. And this is really, really efficient. Yeah, coming to form. So we see now 3D printed houses are already started, but we see a lot of potential, especially in protective structures and infrastructure construction. For example, here we won prizes with the so-called flow wall. So we are able with our engineers from coastal protection, so that they can calculate, depending on the depth, the impact energy on such a wall, and then the form finding can be done so that the most of the energy gets dissipated, not by mass, but by the shape itself. And this is ideally for 3D printing. And also we work with environmental engineers to how we can recreate them. This is the rendering, of course, yeah, but how we can give back spaces for birds, for example, to integrate also spaces to bring back our structures to nature. And this is the add-on printing, so that we, instead of today, most of the slabs in concrete constructions are 25-30 centimeters thick because the formwork is the most cost-intense part. And we reduce again the slabs to 6 to 8 centimeters and print on top the rib, so that we can get back also this nice articulated underneath sealing sites like PVH we did in this Getty Wool factory. Yeah, and continuing this kind of design, you could also then, like I said before, so we are able now to, if we have a floor plan, we can vary the columns. When we vary the columns, we get immediately the thickness of the ribs and the reinforcement. And so this is an integrated system of design and manufacturing. The second option, not concreting running first, but reinforcement running first. Here, an example done from my colleague Norman Huck in his project in the TRR. So the fiber winding on a steel frame, and then you just need to spray on top the shotcrete, and of course it depends on the thickness which is needed. Then gives then really nice objects like you see here. And you can imagine those to bring them together also to shell structures. Yeah, so imagine form. So, you know, maybe the Foreign Office architects Yokohama port terminal, which is done in steel folding structures, which could be also done in concrete construction. A new development we have is the injection 3D concrete printing. So we print in the matrix in another medium which has the same density. So then immediately it keeps its position stable. And here we had an exhibition in 2023 at the Venice Biennale where we showed this bridge, this small bridge we assembled here. So the second track, high-tech processing and low-tech material. So if we use concrete, then in its pure form, then we use high-tech concrete material, ultra-high performance concrete. But if we use a low-tech material, then we can, for example, work with recycled concrete. And recycled concrete, we have one technology is called large particle 3D printing. So is that we try to minimize the energy you bring in the recycled material. So most ideas go to mill it really fine to get the recycled material as close as possible to the original material. So we go the opposite direction. We say we do it as big as possible to not bring in so much energy in the milling process, and try to use then the ultra-high performance concrete to combine the recycled materials and the ultra-high performance concrete. And we build up this structure. It's a particle bed 3D printing. So, and then we unpack this. And you see the material which is not activated by the shotcrete matrix falls down, and then we do a post-processing with our milling unit and make it nicely and clean from the surface. And this is also where we see high chances in this kind of hybrid processing. So the question is how precise you want to get with the 3D printing, with the additive manufacturing, or how much precision you can bring in later, after, in a post-processing. And yeah, you see it's quite a nice object. And this is like I said, so a proof of concept where we start. This is our starting point, and then we develop further the process by doing fundamental research and try to identify the layers. The other track, the low-tech material, is just our earth material. So using earth material is highly traditional. So thousands of years in all parts of the world, we have earth material, and there have been developed different technologies. We focus on round earth, and when you see here the round earth process in relation to concrete, we have the granular material, and we don't add cement, we just add clay and water. And it's totally different. So here is not hydration, no chemical processing which glues the particle together. It's a physical gluing. So you activate the Colombian forces between the water and the granular material. And this is then also why when you deconstruct later on earth structures, you can use the material again. So you can fully activate again its physical binding forces. And again here, you see, you can say it's just a manual compaction. No, it's also much more. All the sands are also in here. So they compact the material, but they're also here, and they see and they get the feedback from the material when it's maximal compacted. And we did the interesting thing is here in the traditional earth construction, because the material already is hardened after compaction, and then you immediately can remove the formwork. This is different to concrete construction. So this is a kind of climbing, minimum climbing formwork. And what we are doing today is that we use this formwork construction from concrete construction. So we do a separate, a new process which is not needed. It's quite the opposite. The material has to get dry, and this hinders the drying process. So we have pneumatic rammers, but we have this formwork, and we said we go back to the origin. So this is the original tool, and we combined ramming and formwork in a so-called active formwork. And you see here, this is now where we also start to automate the filling, and we go now to set up a startup which will try to bring this into the practice. So there's the compaction. And the compaction energy, we do a lot of research on the dry density of the material. So we want to minimize the water, the added water, because then as more water you give in, as more drying time is needed. Yeah. Here you see an image where both is working together. Then now we start also to work with shot earth. So from shotcrete to shot earth 3D printing. And here we add fibers in the mix. So we have this fiber cutter, which is added here. So that you see here, so a long fiber is cut and integrated in the matrix. You can mix it in before, but then it's really difficult to transport the material, or you can bring in the fibers during the application of the material. Yeah, and this is also how we think on how we can use this kind of technologies in a mix of shotcrete and shot earth for fuel protection, for example, so that our shapes are really dissipating the energy and not resisting in the classical way. So finally, a few slides, what's next? So I already showed you, so that we go more and more now on the digital construction side and bring our processes in environmental conditions. The interesting thing is that industry starts now to think on Industry 5.0. I don't know if you have heard this, but it's that humans get brought back in the processes. So from Industry 4.0 to Industry 5.0 is the network of human-machine interaction. And we say construction, each construction site is different. So we always will have people on site. And we step immediately into Industry 5.0. So we are a forehead of the other industries. And you see here our robots working on site, so they can start to print. So, but also we are able to measure the hardening process. This is one of the first tries. But also then humans, by augmented reality, we bring in, for example, reinforcement integration. It's much easier to use the flexibility of our robot arm. So we just need to take it and position it on the green line instead of programming a robot to pick and place the reinforcement. So this is one thing we go for, especially in the reinforcement process. And also the functional integration. So we have a lot of functions which we can integrate. You see here not just the reinforcement, also cables and so on for electricity or heating and so on. And with having these digital models, you are also able to control with this mixed reality not just the process but also beyond. So in the later stage of use, if you want to screw a hole, something like this, you immediately know where you could screw or not. Yeah, and finally, for the newest thing in design, like I said, we see a lot of potential in infrastructure construction, and we have now running. It just started called elevated mobility, so that we try to bring into cities in the traffic hotspots where everything is normally based on the ground floor, maybe the underground we have, but we have not really elevated, we have not used the elevated space. And so we start to look for hotspots. We are able to digitize, to do a form finding, and then also this is now just an early study where there's no green in, but also we will plan to recreate, to get recreation spaces, not just lightweight traffic like bikes and pedestrians, but you can imagine, so that especially in infrastructure, the third dimension is a topic which is not really introduced yet. Yeah, thank you for your attention.
I think you stay on for some questions, I hope, yeah. And I want to ask maybe whoever is in the room here, any questions to the talk? I can bring you maybe the microphone.
Yeah, thank you for sharing your work. I was just thinking in your research, how much is coming from the understanding of new technologies and all the tools available and new kind of perspective of those tools, and how much is coming from, if there is a sort of merging point between that and the understanding of the traditional way of using earth, using all those components. In what is in your research that the role of that and how that is implementing the functionality of that?
Yeah, that's a very good question, because I see it with my students. Christian mentioned, so in 2019 I decided to step out of the practice because I'm not interested in this boring right-angled architectures and structures anymore.
And but I see that most of the ideas is coming from the experience. So you really know how traditional construction works, and then with the new technologies, immediately I see what you can adapt in which kind of processes. And the young people, they have no experience, so they are able to control and to do the path planning and so on. But the initial idea is often coming from the experience. So the understanding of the traditional work, for example, also the ribbed slab, you know. So the ribbed slab is something which we lost a little bit. So we just go for flat slabs because of the form of the ribs. But to bring the ribs back is one thing, but when you understand also that it's a single span rib, so that you don't need the whole section over the whole rib. So with 3D printing, you can also form the rib according to the bending moment line, and also the reinforcement integration. So this is something which is you need to know how construction works, yeah, or the plate with steel, you know.
It becomes also the formal expression.
Absolutely, yeah. Sure, Andreas.
Thank you so much for your presentation. It was really incredible to see how the industry is developing in this digitization of processes. Personally, I think we're a little bit behind with other industries. We know that architecture is really slow in adapting to the technologies. We've seen the automotive industry adapting rapidly in certain things. We've seen other industries, the fashion industry, whatever other industries exist out there, adapting faster to these kind of new technologies. In my question, though, it's also a matter of trying to figure out what kind of materials are going to be used in the expansion of the global population, as you mentioned. We've seen that the population is going to keep growing, but in reality, it's not going to grow in Europe, not in America as well. It's going to be primarily in Africa and then Asia. And so, in my kind of question is, what kind of materials they might be used down there? Is it concrete something that's going to be available to them? Is it going to be ramp earth technology that we're going to have to adapt to? How is these new technologies going to adapt to the existing industries of production? We know that there are specific ways that we do things in architecture and buildings industry. How it can compare with prefabricated components in terms of the numbers that you have to produce? There are so many questions that I would like to, if it's possible, to give us a kind of your personal opinion about the comparison with the existing industry and how you would expect these kind of technologies to adapt over time.
Yeah, this is also a very good question. Thank you. I was thinking a few years ago when we started with this kind of research it's already 10 years ago, that this is much more disruptive. So that means that we will substitute more existing technologies, but now I have to learn that it's really slow, our industry, but this is one thing. But the other one is that we have also this really complex ecosystems. So that means on one side, we have huge industrial players like the cement industry, which want to keep their track to just deliver the cement for the concrete industry. That means we have to use a lot of concrete again. On the other side, we have construction companies, or 90% of the companies have less than 20 people. So they are not able to buy a robot, a printer, just to experiment. They want to have technologies which work, you know. And this is the thing which is really difficult. I see we start more to identify let's say single process steps to integrate. For example, the slab. This rib slab is something which you could use in prefabrication. But to be competitive, if you go just on a slab level, so we can deliver a rib slab, and you are immediately competitive with the other industry, prefab industry, which are cheaper often. So we have to enlarge, let's say, our market profile. So we say we have to start earlier. When we get a slab, we do also the design. So let's say we take from the architects and the engineers at the end. So we much earlier we take the slab, we do the elementation, also the concept maybe on design for deconstruction, so that we integrate thinking on post-tension principles, so that we can use again these things. You have to find new tracks which are much more innovative as the existing ones. This is what we are working on, and I see the most chance now in go into this protective infrastructure. So we get a good feedback on this coastal protection, on this food protection, on these things, maybe on bridges. There where the complexity of design is really coming from an impact, is not from a design idea, do a nice curved wall in a house or a roof. It's coming from a need, you know, so and landscape integration and customize situation and landscape. So let's say the wind towers, they are the same. They stand all over the same, you know. So Holcim and Cobalt, they started 2-3 years ago to do the first 30-40 meters in printing, because the diameters are too big to transport, and then come with prefab. So also this hybrid combination of on-site and prefab. So this is the industry is also not used to this. They think either in prefab or on-site, and we see we have to find our markets in these interfaces between the players and the technologies.
Thank you so much for the time. And I will continue, but we can do it afterwards.
Yeah.
I want to leave space for other questions.
I have a question for you. In particular, you mentioned the base research, that we are kind of slow, or we have to adapt to base research or fundamental research.
Fundamental research, yes.
So with our students in our lab right now, we are experimenting with earth materials, but also with local waste. So kind of how can we reintroduce or actually divert local waste from landfill and actually add it to new construction materials. And then the other one is geopolymers. So kind of how can we introduce a chemical polymerization, mineralization process that allows us to do ambient temperature curing, etc. The problem that we see right now is that, in both areas, so waste materials in particular, but also in general polymerization processes, that there is no standards. Kind of what standards do we apply to 3D printed earth construction first? Second, what if we add actual materials whose properties are actually unknown? And the same is for polymerization. If we use concrete, which in its performance is actually sometimes lower than geopolymers, when we use those standards, they are not really the standards of the materials we're using. So we're basically we are hijacking standards that are written for other types of materials, but not the ones that we're actually right now developing, testing, and executing. Right. So this is kind of a big, I think, global problem. We, if you do a literature review, you find dozens and dozens of papers where people dig in different areas. Everybody refers sometimes to the same standards, which are not the standards of the material. So you have to actually, what we're doing right now is we're doing a catalog of standards that actually apply as close as possible to those materials, and develop a workflow, at least of from the sourcing to the mixing to the performance testing to the actual functionality testing, and then actually to the 3D printing, and we have all the things of radiology testing. So basically, you have to be no more an architect, but you have to be suddenly, you have to have a team of chemists, of biologists, of civil engineers, and you have to go actually not on material, and you probably have the two. You're not on a material surface, but actually we're looking at nano, microcellular, microstructures, and then a macrostructure. So it's all one fluid dynamic process. And I think there is a lot of knowledge out there that needs to be built first before even you can actually move to scale, because the issue is also the experimental materials, and how do you actually get them to scale and afterwards, right? So it's a difficult problem.
No, it's very, very, very clear. And I often say the architect of the future is not a person, it's a team. So coming from a person, the knowledge is not able to contain in one person's head. So you need really this team. And exactly, we are working this different scales, but also here we have to think, let's say more hybrid. So in a material scale, we try to use the CO2 footprint, like you said, by using alternative binders or using the earth material in its pure delivery from earth. But then also we have the scale of the mesoscale of the elements. So there we try to optimize the inner structure of the reinforcement integration, whereas really compression, whereas tension, so how to guide the forces. And then also on the mesoscale, the system scale. So that means how we can design for deconstruction, how we can find new guidance of force flow between the vertical and horizontal elements, between slabs and columns or walls. But I think also that in related to norms and regulations, I mean, when we go 100 years ago, yeah, but when we go 100 years ago, you know, those guys of Maillard and later on also Nervi and Freycinet, they had not these norms and regulations. So they tried to understand material, process, and form, and they took the responsibility for this. The norms and regulations is a creation of the last decades from us. So I'm not willing to take the regulations. We work in this idea of unifying those three. And for me, it's important always not to develop a material as a material, like I said. So when we always combine it in the material process interaction. And I see much more that in the future, for example, we have to find regulations for material process combinations. So that means shotcrete process has its defined materials, has its defined control figurations, and not this in general regulations, how we are used in construction. And this is like the other industries are doing. A car is not in a general regulation for how to construct a car. No, a car is for itself designed, and they get this Zulassung. So they for a product, you know, they apply for getting the regulations. And we have to think much more in when we have a column slab system with shotcrete, then we can try to get the regulations for this system, not for, in general, the shotcrete process. We work more on this.
So you would, if I understand correctly, you would test the actual construction.
Yeah, of course.
And the elements of construction, not necessarily the material itself. In that sense.
And would say, for example, we have a system for a 7-meter span, for 10-meter span, and the thickness is this. I go much more in thinking more in a product for structured systems, and
Yeah, I'm thinking also that if we use waste material as a resource, I think the challenge that we are seeing is also that, for example, with AI, that we're working on it right now as a base strategy to actually develop a predictive model. So you actually, because you have a certain testing regimen, so you know what materials you test, you know how they perform, what kind of mix you have. So then from there, you can start predicting, if I was use this percentage of this material, could I get this kind of type of performance? Right. And I think building into this kind of intelligence early on, maybe, looking into alternative materials, etc., might be a potential.
But you could also think on separating the functions. So that means we are also used, for example, to do a wall in concrete. Then it's the function of a wall element as to divide spaces, and as a structural element to take loads. So, but for the separation of the space, you don't need the whole wall in fully in concrete. So the question is also, maybe this, we are working also on this by this injection 3D printing, is not that we just print into a fluid to make a form. We also print concrete into concrete to, for example, use recycling concrete as a basic filler in the formwork, and then inject defined where structural high sophisticated concrete is needed with ultra high performance concrete. So we can print columns or diagonals in the normal formwork construction. So this could be also interesting with waste, you know. Then it's you separate the functions and you use your regulations for the structural ability of the and for the others is fine.
How does the research that you do trickle down at TU Braunschweig into, I think that's a question.
How much does it?
I talk sometimes with our colleagues
that
teach structural design, most structural aesthetics here, and they teach the traditional materials, so concrete, steel.
Also my colleague.
Sometimes timber, glass, of course, less stone, or maybe never stone, earth not existing, and kind of now how do we actually change the curriculum if we actually think into alternative production processes, alternative materials, etc., because we have to start from at a lower level. Do you have any influence in Braunschweig? How trickles down to your colleagues in the structural classes?
Yeah, we have. It's this is also, let's say, why I choose to go to Braunschweig. We are one faculty, engineers and architects. And I'm, as a structural designer, located at the Department of Architecture, but all the collaborations are with the colleagues from engineering, and we have joint master thesis and so on. Though the students force us, so they want to work in this stuff, and they are interested, and it's slowly, but it develops. Yeah. Good.
Very good.
Thank you very much.